send you an email about Ramadan schedule. So tomorrow, if it is Ramadan, it is declared tonight that it is Ramadan, then the test will be at 12 o'clock, not 12:30, because the schedule changes. Okay, just to show you.
And 40 minutes only per class.
Yeah, but we have 3 classes consecutive, so I will still allow you to take 15 minutes, and if you need, maximum 1 hour. We're stuck. Okay, thank you. We're back. No, that's not what I want. Ready. So that's how it looks like. Right after the prayer break tomorrow, which used to be 12:30 this time. Well, it used to be. Today or last week, that's the way it was. Okay. Any questions, or shall we move on to more stuff? Yes? Move on? Single phase? Or you have any questions for tomorrow? No questions? Want to go home?
No, I have a lot.
Yeah?
It's not fair.
I've seen the questions, the submissions. And again, you need to be a little bit concise in your answers. It doesn't have to be a book, but it shows whether you understand or not. I've seen some explanations that were gibberish. They don't make sense. Most of them were okay, but not complete. What's your question?
On a squirrel cage
Squirrel cage.
and the one motor, like both cases. Squirrel cage, the current is on the cage itself.
What creates the current?
Yeah. No, where is the current located?
In the cage?
Yeah, and the cage it's in the cage itself,
Yes.
right? On the
Yes.
bar, on the
Yeah.
wound,
Well, not in the windings.
on the winding.
There are 3-phase windings. Yes, yes. The windings themselves act like the squirrel cage.
So the current will be on the winding itself.
Yes, of course. Because it's the windings that's where you induce the current from the stator rotating field to the windings, to the rotor windings. Right?
Yeah. So that's one motor.
Hmm?
Same as like the one motor, the DC one. Yeah. Okay.
Like what?
The first DC motor we did.
Yeah.
Same thing.
Well, it's not. You mean it's similar?
The current.
It's
Where
not
is the
same.
current located?
No, you see, in DC, the armature current is rotating in the stator. But in the wound rotor,
The wound itself.
it's an induced current. It's not even a field current.
Induced.
When you say a field current, it's something that we are supplying directly. Right? So this is current which is induced from the rotating magnetic field and the stator. There's no current that we're supplying to the rotor whatsoever, even though there are slip rings. Don't let the slip rings fool you. Slip rings are there only for connecting external resistors, right? These slip rings for 3-phase. Okay?
Oh, okay.
So we're not supplying any current neither to this one is obviously it's completely disconnected from the external board. It's just the cage inside the motor, sitting right inside the stator windings, and the action of rotating magnetic field causes current to flow, causes torque to be produced,
for the rotation.
Yeah. And therefore, it reaches very close to magnetic to synchronous speed, but never reaches it. Right?
Because if it does, then they will have
Why is there
no
well,
current, no.
Yeah, we're not even talking about E counter EMF here as we
Yeah.
did in DC motors, right? What makes the current so big in the beginning? Starting current.
Because the rotor isn't rotating. I mean,
Correct.
The
But
one
so
is-
that would
Yeah, because the speed is very much, the difference in speed is a lot.
absolutely. So there's
Yeah.
very high speed
Differential.
of cutting the lines. The lines of the rate of cutting the flux lines is very high. So therefore your voltage is maximum. Remember that equation? E equals BLV.
Yes.
B is the strength of the field, magnetic field. L is the length of the coil.
And velocity.
These are fixed. Right? Strength of the field coming from the stator. And the length of the conductor is fixed. The only difference is the speed. The rotor in the beginning is sitting there, doing nothing. So the magnetic field is rotating at synchronous speed. That's a lot of cutting. That's a lot of current flowing in the rotor. That means a lot of torque. It gets it going. Now, as it starts going, the difference of speed goes down. So the rate of cutting goes down. So the velocity V goes down. So the induced EMF goes down. It's not counter EMF, it's induced EMF, right? And then it keeps doing that until there's just enough current to keep it going. There's just enough difference between the rotor speed and the synchronous speed to keep enough current to provide enough torque to keep it going without load. So what happens when you increase the load? When you put more load on the motor, what happens?
Speed will decrease.
It will slow down,
So we'll get
As it slows down-
more cutting, so more current and speed up.
more current, and we won't necessarily speed up. There's a little bit of change in the speed itself to make up for the increased current. So you need more current to carry that load.
Oh yeah, yeah. More torque, basically.
You need more torque, because now you're dealing with a heavier load, right? So that's why in induction motors, we're not concerned about accuracy of speed. If you're any application that requires accurate speed control, you need synchronous motor.
so basically it's gonna slow down until it's rating. If you went above the rating, it's gonna stop.
That's
Not for induction.
Not enough for induction.
Induction never stops.
no, the
Of
slip.
course, it can lock the rotor. If you go way beyond, or it can burn. Because you see, when you increase the load on the rotor, that means more current is flowing in the rotor. That means more current is flowing in the stator. Now, of course, it has a maximum voltage rating. Remember that nameplate that we looked at before? That nameplate tells you what's the full load amperage. So if you keep increasing the load beyond the rated full load current, what's going to happen? It's going to heat up more than it's allowed to. And if that is not, of course, usually motors have overload protection. So the overload protection will eventually cut the power, stop it altogether. It's not stopping because it doesn't want to go, but you're overloading. So if your protection is working properly, it will guard it from being burned. If your protection is not working, you keep going on adding more load beyond full load current. Eventually, it will burn. The insulation on the windings will melt.
Oh yeah.
There'll be a short circuit.
I think what he's talking about was synchronous. Synchronous, if you too much load, then it slip.
Well, yes. But,
Yeah.
you know, in our
Yeah.
discussion, we're talking about induction.
Induction, yeah.
Right? But synchronous, there's pull in and there's pull out torque. Pull in torque is what? And always think about it as what? Pull into synchronism and pull out of synchronism. That's why it's called pull in and pull out. Pull in means
It's the speed that is needed to.
not the speed,
The rotation itself,
not the speed.
the field
it's the
itself.
torque that is needed, so the motor could reach synchronous speed.
Yes. So it's being pulled into synchronism by the action of magnetic
Magnetic,
attraction.
yeah.
That's why in synchronous motors you never turn the excitation on until you're at least 90% of synchronous speed. So otherwise, what happens is that the the forces, magnetic forces are rotating too fast for the rotor. So they are pulling and pushing, and they are working against the squirrel cage. So if you excite a synchronous motor too quickly, you're going to hear a big noise, things like that. I don't know if the experiment that in other experiments, in other cores, it actually takes you through that step. Tells you, you start the motor when it is excited and see what happens. Big noise. Because it has a squirrel cage, it's trying to move it. And then you've got this rotating magnetic field, it's pulling and pushing at the same time, very quickly. So you don't excite it until it reaches at least 90% or more of the synchronous speed. And then you turn it on. The magnetic attraction and this difference of speed is enough to pull in the poles of the rotor with the poles of the stator. So now they are in synchronism. And they keep that way. Now, when you start increasing the load, when the motor is not loaded, they are perfectly matched, 1 to 1. When you start increasing the load, it's like a rubber band between the poles that are being stretched. So you increase the load, it stretches a little bit, so the stator field is going a little faster, a little ahead of, not faster. Still the same speed, but it's just stretched a little bit. And that continues. You add more load until the pull-out torque. Pull-out torque is the maximum load you can put before.
It slips out the
It's not the one that causes the breakout. It's just before the torque required to pull out of synchronism. If it does pull out of synchronism, right? If it does not have a squirrel cage, it will just go close to standstill. If it is equipped with a squirrel cage, at some point below 90%, it begins to fight against itself, if it is still excited. So then with a synchronous motor, as long as you operate it within range, this is true for any motor. But with synchronous motors, it has some synchronous motors are not even designed to be loaded with anything. They are just used as capacitors.
For correcting the power factor.
For power factor correction. Because you can run a synchronous motor as normally excited, underexcited, or overexcited. Right? If it is normally excited, it's neither consuming nor producing reactive power. If it is underexcited, or it's like a inductive load. So that means it also requires reactive power in addition to the real power, because it needs to make up the difference. Underexcited means what? There's not enough magnetic flux in the rotor to provide sufficient amount of magnetism to pull in the poles. So it borrows more from the reactive side. If it is overexcited, it means more excitation than it needs. So it gives up some reactive power. That's why it becomes higher than 1 power factor. Underexcited, less than 1. Overexcited, more than 1 power factor. Normally excited, 1. And these types of motors that are used as capacitors, they don't even have any connections to any external load. They just run like that. It's just a capacitor, just a motor for power factor correction. Of course, capacitors are simpler, right? Capacitors are not as adaptable to changing loads. Motor is. You can, by adjusting the excitation, you can change how much power factor correction you want to introduce in the system. Because again, if you look at systems, their power factor doesn't stay the same all the way through. It also depends on what equipment they're running, what time of day, what kind of production scenarios they're going through. So that's the main advantage of synchronous motors. More expensive than capacitors, right? Because you've got moving parts, you've got maintenance. But that's a decision that has to be made at the design stage. Do we use capacitors or do we use synchronous motors? Is it worth it to pay the extra cost to have more variable control on the power factor correction, or are we okay to run with just aiming for 0.9, for example. In the worst case, we're gonna get 0.85, satisfy kahrama. In the best case, we're gonna get maybe close to 1. You never get close to 1, you don't want to be close to 1.
What's capacity?
Capacitors are used for power factor correction, right? You know that, you've studied that, right? In ET. Did you do it? ET 1131?
Power correction.
Power factor correction with capacitors. Very interesting topic. And very easy calculation, but you need to know it. You need to practice it. And companies, they invest money into these capacitor banks for power factor correction. And of course, if you really want to go into the details, you have to know how much it costs if the power factor goes below 0.85, because Kahrama has tariff for that. They say as long as you're 0.85 or more, no problem. We're not going to charge you for reactive power. But if your power factor falls below 0.85, you're going to have to pay or make a power factor correction. So you as the engineer, you're going to come back and say, okay, well, what is our profile? Give me some data. You can't work without data in engineering, because then it becomes educated guess. And you better know where you are at. Every time you do some study or you do some calculations, better know where you are at, where you're standing, documented very clearly. Am I working with historical data where I can make better estimates, or am I working in the dark? And therefore you need to say, this, no precedence for this, for what we're doing, and so therefore we're doing the best we can. But if you have the data, and then you can see, okay, it costs us so much per year to pay for our power factor, which is 0.7. How much will it cost us to put a synchronous motor or capacitor banks? You have to calculate first how much you need. How big is the capacitor bank or the synchronous motor? And then, okay, how much is it going to cost? How much will the installation cost? How much is the maintenance? And then you have a yearly figure. How many years will it take to recover? Is it better to continue to pay kahrama or to put capacitor bank? Or see, in the college, most of the work that you're doing is technical in nature. But in your capstone, you need to get into the break-even analysis. And that's how projects work. Projects need to worry about what? Scope, time, and cost. Quality. Every project. And we don't do projects just because they sound nice. You always do, feasibility study and payback analysis. Okay, any other question? Should be very clear on induction motors and synchronous motors. All the issues that we have talked about, right?
What should I know about wound rotor motor? I know like the only difference between
Why do we use it, first of all?
Yeah.
Why do we use it? What's the main purpose? See, synchronous squirrel cage motors are beautiful. They are low maintenance, reliable, low cost.
But high initial torque, right?
No. Squirrel cage, they have lower initial torque.
No, we're talking about the wound.
No, but it's, yes. So this has certain features that you pay for, such as reduced starting current,
Yeah, current.
higher starting
Current,
torque,
I mean. Yeah.
also higher starting torque, both of them.
But you can adjust it. That one is like always high current.
That one, class. This is what you have. You're not concerned about.
Yeah.
This is good for high inertia loads. Okay, but this one isn't. So it depends on the application. Now, I want to give you again some hints. How's that? Hints.
Sure. Squirrel is high initial current.
What's that?
Squirrel cage, high initial
Oh
current.
yeah. It's always between 5 and 10.
Wound, no. Wound you can control.
Wound, because you have the external resistors. You can
Control it.
dictate.
Yeah.
Yes.
That's the advantage, or like how you want to use it. Yeah. Okay.
Right. Okay, so I'm going to go through a few items that you need to be aware of. Okay? Okay, various operating characteristics of these three-phase motors. Synchronous motor, what happens between torque and starting torque and running, what happens to the current? brushless, there are, of course, remember, synchronous motors, there are brush type, and brushless. How does the brushless work?
In a small magnet and
Well, yes, it works by induction, and there's like an alternator on the rotor itself, including the rectifier circuit. So the whole thing doesn't need any slip rings or any brushes. That's why it's called brushless. Okay, you need to know the relation between slip, what happens in a motor, whether it's induction or
Wound.
synchronous, huh?
Or synchronous.
Is there a slip in synchronous motor? No.
Wound? No.
Again, my advice to you when you look at the multiple choice questions, don't take them for granted. It's not just a matter of wild guess. You need to look at them carefully. Oftentimes they are close to see whether you really are confident in what you're saying or not. Of course, statistically, you have 25% chance as a wild guess of getting the answer correct. But don't depend on that. I mean, the whole thing is you showing your understanding. So don't take them as just something to get out of the way and finished. So I told you there are two parts. First part is 20 multiple choice questions. Second part, there are 3 questions. Two of them have part A, part B. And then the second one has no parts, just one question.
calculation.
One slips.
Which type questions, yes. Part 2.
One motor slips as well. Is that one?
Part 1 is 20 multiple choice questions on both
No.
synchronous and induction motors.
No, I mean the slipping.
Yes.
Squirrel cage slips,
Yeah,
and one motor slips.
huh?
Wound motor.
Of course. Any
Yeah.
induction motor has slip.
Yeah. But the synchronous cause look.
Yeah, synchronous is not induction. We might have an induction operation to get it started, to get it going.
But when there is sync, there is sync.
But it works mainly magnetically.
Yeah.
But it needs to be brought to close to synchronous speed before magnetic force is effective, right? You need to know what is pull in, what is pull out. I just explained. I need to know about the issue I talked about, exciting, when to excite synchronous motor.
When they're close to synchronous speed.
Yeah.
As close as you can get. Synchronous speed.
Yeah, you need to know the load characteristics of both induction and synchronous. What happens when you increase the load? What happens, like I said before, with synchronous motor, what happens? With induction motor, what happens? The same discussion that we had, right? Synchronous motor, when you go beyond its rated load, it will pull out. And with induction motor, what happens? It will increase the current beyond its full load current.
Synchronous though is for steady load, right?
Synchronous, it's for loads that require
Constant speed.
Constant speed or yes.
So yeah, irregular speeds are not good for synchronous.
It will never be irregular, but it can pull out if the load has exceeded its rated load. It can pull out of synchronism.
Can
Pull out of synchronism means if it's not equipped with a squirrel cage, it will go back
yeah.
to 0.
Yeah, but if we use it as synchronous and like a escalator,
Yes?
it's not good, right? Because it's always or no wait.
It's constant speed.
Does it work with variable loads?
Yes, it has a range of load from 0 to something maximum.
Oh, okay, yeah.
As long as you're within that range, no problem. But if you exceed the maximum load, then you're running into pull-out torque.
Yeah.
Pull-out torque means if it's not equipped with a squirrel cage, it will close back to 0.
Zero, yeah.
If it is equipped with a squirrel cage and you fall below 90% of the rated speed, it starts fighting. The squirrel cage is fighting with the poles, because now the poles are going much too fast for the rotor. And the poles, the rotating magnetic field, or fields, are going so fast, they pull and push very quickly. And so the rotor doesn't know where to go.
So the resistance goes up in an induction motor, it will go, the current will go
Yeah.
beyond its rate.
What's that, say again?
And the resistance goes up,
For what? For the rotor, my wound rotor?
and
There's no resistance,
When
okay.
the load, sorry.
When the load goes up,
The load goes up.
so don't say resistance, it's the load, yeah?
Yeah.
Mechanical load.
Mechanical load goes up, the current is gonna go beyond its, Okay.
Not necessarily. If you're within the range, it will not go
Yeah.
beyond its rated full load. Full load current means the maximum current. So that happens at the maximum load.
If you
So
exceed
as long
that,
as you're not exceeding the maximum load, the full load current will not be exceeded. But if you exceed, if you apply more than it is designed for, you exceed the full load current, that's called overloaded motor.
you will exceed the current.
Okay? All right.
Higher load, higher current. Basically. And the one motor resistance controls the initial.
current.
You need to
Current.
know about the rotating magnetic field. How is it produced? Right?
Well,
The magnetic field. How is it produced? In three-phase motor. We said it so many times, yeah, Mr. Kahima. How is the rotating magnetic field produced?
there are three parts, right?
Yeah, three windings.
Oh yeah, they're always 120 degrees apart.
The difference in the angles.
You have physical differences in the angles of the windings, and you have electrical
Different.
difference. Same thing. And like I said before, you know, magnetic flux lines never cross each other. So that what happens is you get a resulting overall magnetic field. But because these north and south, they're not staying at the same strength because it's AC. So they make stronger and then weaker. The net result is that it's rotating magnetic field. Remember last time I gave you the example of if you take, here's north, here's south, here's north, and here's south. Normally we would say north to south flux lines, right? That means they're crossing. This is not allowed. So what they do is they intermingle together and they bring up a resulting magnetic field. This is north and this is south. And there's only these lines. That's it. These lines don't exist. Now imagine the north and south are not staying at the same strength. At some point this flips back to being north and this is south. The same thing here. So the resultant field is going to follow. At some point you have north and north here. It's going to be, so the resulting field will be like that, north and south. And that's what produces the rotation. Because they have phase angle to them. They're not pulsating at the same time. If they are pulsating at the same time, there will be no rotating magnetic field.
Yeah.
That means the field will just stay like this, it will just flip back and forth. If these are pulsating in synchronism. But if there's a phase angle difference, this will be rotating. The resulting. Same thing, this is easy to visualize. When you have three phase, and instead of just these four poles, you have two more. Right? But still, they will all intermingle together into a common north and south. Because all of them are pulsating at different phase angles, the resulting field is actually rotating. You don't have to tell all this. You don't have to give this example. You just need to know in your mind that the rotating magnetic field is the result of the phase angle difference between the voltages.
And the physical.
Well, the physical is what produces
Rotation.
the electrical. Physical windings are actually
Yeah, there is a physical
Spaced. The
spacing
windings themselves, yes.
and electrical spacing.
Yeah.
Both of them together create the rotated magnetic field.
Exactly. Okay?
Difference between the angle and inch.
Reduce
A
voltage
physical,
starting. How many methods we talked
electrical.
about?
Electrical 120 degrees apart.
Reduced voltage starting. We said resistor method, auto transformer, what else? Y delta, and then part winding.
What is that?
Look at the PowerPoint, guys. Remember the PowerPoint?
Reduce the voltage.
What's that?
That's for reducing the voltage.
Yeah. How do you reduce the start? Well, why do we reduce the voltage? Starting
Current.
to to reduce the starting current.
Current.
To limit the starting current. So what are the methods? Well, by the way, we had discussion about this.
For
Just went to Tabor. Remember we thought these were contradicting? Here it says, as the rotor speed increases, its frequency and reaction decreases. This means that increase in IR. Here it says reduces IR. There's actually, in the operation of the motor, that there are competing forces. That's why you get this kind of graph. Your torque is not fixed. Your torque, for some time, it goes down because one of those forces is dominating, and then in another phase is actually going up. So the other phase is going higher. And I'm taking that, by the way, in question 4. This was what brought this discussion. Question 4 in the last question, part B.
Last question.
What it says, if your frequency goes up to 60 hertz, what happens to the RPM? That's clear. And I gave you a clue. I said, generally speaking, power out is going to go up. That means the current will go up. But the question is a little bit too advanced for all of our discussions. We don't want to go even to the details of why this curve behaves like that. But sometimes in these motors, they're very simple, right? Rotating rotor, and then you put some load to it. But when you look at the detailed electrical characteristics, sometimes they get a little bit challenging. It's not as easy to digest. For example, why is this curve like that? So we didn't really go very deep into this. So I think that question, part B, I'm just going to take it out altogether because it's not fair. That question is a little bit too deep. Okay? But that is not wrong, is what I'm saying here, Mohammed. That previous slide, there are competing forces at different stages of starting the motor itself. Let me go back now to starting methods.
that reduce voltage, you use the
Double
resistor.
square cage.
Hmm?
Double squirrel cage.
No, that's not for reduce. That's for improving the starting torque. Double squirrel cage is for improving the starting torque, and also not limiting the speed when you're at full. Because if you, that's what happens with the wound rotor motor. We turn in the resistors at startup, and then when it's close to full speed, we short out. So it's working like a squirrel cage motor. Minimal slip. Because increased resistance means what? Means more slip. That's why wound rotor motors are also used for variable speed applications. Wound rotor motor gives you more control over the speed. With squirrel cage, khalas, it's it. Whatever you got, you got. Your slip will change as slightly will change as the load changes up or down. But with the wound rotor motor, because you have these external resistors, you can adjust how much resistance you are allowing. You can control the torque and the speed, as we have seen in the previous graphs. This is the
Double square عشان slip, right? Double square for the slip.
No, the double squirrel cage is for improving the starting torque, because the starting torque of a single squirrel cage motor is low. So you got double cage, right? Double cage one inside the other to improve the starting torque, and at high speed it will release. It basically introduces higher resistance. One of the cages has higher resistance than the other.
Yeah.
One of the cages takes over in the beginning. The other cage takes over towards close to the rated speed.
Oh, okay. So okay.
Yeah. But I want to go to the starting. I'm not going to ask you what's NEMA, but you should know. If you go to industry, you need to know what's. I'm not going to ask what's class A or what's class B. You should know them. At least, even if you don't memorize them, which I'm not expecting you to memorize them, but at least when you see class A or design B, you know where to look. What does that really mean? And of course, we're just touching the tip of the iceberg. We're not really going very deep into all this stuff, but we know. You at least know which applications are relevant to these various designs, and also the enclosure ratings, IP ratings. All right, so this is the first method. Reduced voltage starting or reduced current. The primary purpose is to reduce the starting current. Again, when you talk about reduced starting current, what we're really concerned with is what?
Voltage.
With large motors. In small motors, it doesn't matter. It's just 6 times 0.5 amps, it's not much. Just 3 amps. But if you have a huge motor, like 2.5 megawatt motor, that's huge. You need to be very concerned about the starting current, because it could affect the system. So this is one method, is the primary resistor starting. This is auto transformer starting. Part winding, reduced voltage starting. And then we've got white delta. Okay, and we'll talk about these control circuits.
And why
As well.
delta? Huh?
This is the one that we did not really cover. This is the solid state starter. So this is now gets into computer chips and all that stuff. So it shows you here, this is cross the line or direct online starting, and this is solid state reduced voltage starting. So the voltage at 100% with direct online, but with solid state, the voltage is increased over time. Starts much lower, so it applies reduced voltage. What else? Look at the current. Current is 6 times with direct online, but with solid state, it goes up gradually and reaches its operating or rated current. What about torque? Starting torque is very high in the beginning, but with solid state control, it actually ramps up, overshoots a little bit, and goes back to operating speed.
Same, zero.
Very quick with the direct online. But with the solid state, it takes longer. So it depends on the application. Normally, it doesn't matter if you wait for your motor for a few minutes to get started. It's not a big deal. For, like, for example, petrochemical plants or manufacturing operations, not a big deal. That's really it. Now, this is where we go to single phase motors. Okay, so these are the main issues you really need to be aware of. Also resistance, induction motor overload, what happens, reversing rotation of AC motors, 3-phase. We've done it also in the lab.
Switch any 2 poles.
Any 2 phases.
Any 2 poles.
Any 2 phases, not poles. Poles is magnetic poles.
Adreno? What?
Why do we need DC power in synchronous motor?
Because it's not outside.
Why DC? Why not AC?
Because DC is easier to make it. Because it has higher starting torque.
This is an important point.
High torque.
Nope.
No, why DC?
See, in the synchronous motor, if you go back, the excitation current is DC. Why DC? Because I want my north and south poles to be fixed. Yeah, they are rotating. They're rotating with the rotor, but I don't want them to be changing. The stator poles are pulsating, so that the magnetic field is rotating. That's something else. That is something else.
So which poles are fixed then?
Huh?
Which poles are fixed?
The rotor. You see, got rotor poles.
Oh,
and stator
okay, yeah.
magnetic field rotating. The magnetic field, the magnetic poles of the stator windings, right? They are pulsating in strength. They're even flipping. The north becomes south and south becomes north. The net effect is a rotating magnetic field. But for the stator, what is north, I want to keep it north. What is south, I want to keep it south. I don't want my north and south poles on the rotor to be changing. Yeah, they are rotating. They're trying to catch up with the rotating magnetic field from the stator, but they need to be fixed. And the only way to do that is DC. Is that clear?
Yeah.
DC is important to maintain the poles, or to maintain fixed poles.
On the stator rotor or rotor.
Now again, when you say fixed poles, mean their relative location is fixed because they are rotating. But the relative location with respect to the rotor center stays fixed.
So DC is important to keep the poles
Fixed.
and
In the rotor.
And the rotor poles, yeah.
The rotor poles, not any poles, because the DC is in the rotor. That's the excitation current we're providing to excite. What do you mean by exciting, Hamid? What's exciting? Exciting the what?
Start the magnetic field, basically.
Exactly.
Yeah.
Excite the magnetic field. Yeah. So how to control the speed of the repetition.
So,
These are the main issues.
where do we get rotation then?
Hmm?
Before we excite, right?
before you excite, you get the rotation because the difference in the phase angles. And
But the excitation, you don't apply the excitation until you're very close to synchronism, like I said, 90% or more.
Yeah. Where do we get the
Excitation?
no,
No.
the synchronous speed?
where do we get the speed? Because of the difference in the angles. No, actually, in the synchronous
I
motor.
mean, how does the rotor reach synchronous speed?
Yeah, or not before synchronous speed. Before we excite.
Before the
Before you
excitement-
excite, you have to have a starting method.
Yeah, that's what I'm asking.
Because remember,
Oh, the
synchronous motor-
squirrel cage is gonna do it automatically.
Exactly, yeah.
Otherwise, you have. Oh, okay.
synchronous motors are not self-starting, so you have to either equip them with a squirrel cage,
Or
Or-
a starter motor.
pony. It's called a pony motor.
Yeah.
So
Yeah.
a pony motor, you turn it on, maybe it's connected through gears or through the belt. And it gets that rotor going until it's close to just above 90%. When it reaches 90%, then you can turn on the excitation.
And disconnect the pony.
Now, of course, when you see that the poles have caught up and pulled in, that means the rotor has reached its synchronous speed. Khalas. That's it. It just keeps running. Then the pony motor, if it is pony motor, if it is squirrel cage, what happens to the squirrel cage when it reaches synchronous speed?
Slips. It's never reaches synchronous speed, right? Before it.
Synchronous motor, it reaches synchronous speed.
No, the squirrel automatic
No,
alone.
remember, one of the methods of starting synchronous motors is to equip them with a squirrel cage. So if the motor is synchronous motor, equipped with a squirrel cage for starting.
Yeah, but it will never reach synchronous alone.
No, it will, because it's synchronous motor.
If you excite it.
If you excite it,
Why?
But
But
what I'm
before
saying
you, before you excite it, it will never reach it, right?
correct. And you don't excite it until it's close to synchronous.
And it automatically does that because the cotton will be different.
Now, but my question was, what happens to the squirrel cage when the synchronous speed is reached?
It is a synchronous motor.
Huh?
It is a synchronous motor. And
No,
that's
that's not my question. What happens to the squirrel cage?
Wait.
Nothing.
It's stop.
Why?
What's stop? If the squirrel cage is in the rotor, what do you mean stop?
No, if it reaches the synchronous speed, like both
No
of them
current.
are going through the same speed, so it's stationary at that point, so no voltage is induced.
Yes.
No current, yeah.
Don't say
And
stationary. Their relative speed is zero.
Zero, yeah.
They're both rotating.
after that, so one
there's
of them
no
is gonna
current.
slow
No
down.
current, yeah.
The squirrel cage is just happily taking the ride.
Yeah.
It's not doing anything as far as producing torque. It's just
So-
going on for the ride.
Yeah.
It's gonna slow down, then it's gonna, that slowing down is gonna create a slip, then it's gonna keep rotating as normal.
Where? When? What? What?
Synchronous motor.
No,
Synchronous-
for squirrel cage.
No, if you sync it, then it's not gonna slip unless you overload it.
Listen carefully. This is why even in these tests, you have to read the question more than once. Make sure you understand it. Make sure in your mind there's a difference between squirrel cage, pure squirrel cage induction motor,
I
and
think.
a synchronous motor equipped with a squirrel cage. These are two different animals, if you will. One is pure induction motor, has nothing to do with synchronism. No excitation, no nothing. It's just squirrel cage motor. The other one is a synchronous motor where the rotor is fitted with a squirrel cage. To aid what? To aid the starting, because it's not self-starting. But as soon as it's close to synchronous speed, we turn on the excitation, it reaches synchronous speed. No cutting of the field. That squirrel cage is not cutting anything because it's rotating at the same speed as the
Yeah.
magnetic flux. So
But-
no cutting of the lines.
Yeah.
So it's just sitting there. No current, no torque. And it was found actually, with synchronous motors, when there's sudden changes of load, you could get disturbance of the rotor. But with a squirrel cage, it smooths down the rotation. So it's much smoother because if there's any disturbance, it kicks in. There's torque to keep it going. within the range. So it's good also for smoothing out the operation during normal operation. Okay? It's very interesting stuff. I know it's a little slippery, but that's why I had all these videos and all this discussion. If you notice, we've really been repeating some of these ideas over and over again just to get them to sink in. But the main ideas are simple. Again, you need to go through the PowerPoint, make sure you get a good mark on assignment 2. I've seen the results. Some of them are good.
Sir?
So they are marked. Go and take a look at them. And then if you still have any questions, come back. If you want to take them again, by all means. But always remember, I will take only the last one.
Could
Only
you
the
check
last
after
attempt.
my second attempt?
I always check the last one. I don't check them all. So if you do it again and you get a better mark, then I will go and take a look at it.
No, some marks I'm getting 0 out of 1, and I look back to
Out of
my,
11.
No, 0.
Oh
my
yeah.
question.
So those when I say a mark, that means I went in whatever it's not correct, I override it. So go and check it. If you still have any questions, come back to my office. Okay? All right. See you tomorrow.